What, Dr. Davis?
Ah, I'm glad you're here.
What do you need now?
Actually, I just want you to look over some data we recovered from the zombies.
What kind of data?
Well, we figured out that the zombies are predictable.
How so?
They travel in lines.
Lines?
Yes, actually. Simple lines, modelable by simple equations, learned in any high school textbook.
Really?
Yes, in fact, I have an example set up over here.
An example?
Yes, demonstration, you could say.
Where? And with what?
Outside, of course, and with zombies.
Actual zombies?
Why not?
But you know they're dangerous.
Yes.
And you aren't taking the proper precautions.
That's not the point. The point is, this is a monumental breakthrough. We can figure out where they're going now.
Okay, fine. Just show me what you're talking about.
Alright then, right over here.
Here's a zombie I prepared earlier. Yes, as you can see, it's tethered, not able to move. And what else do you notice?
I think I see now.
Exactly. It's a line. And if we overlay a grid, as we've done... here. Some things begin to appear. Things become... predictable. For example, let's take this point as being the origin, where the line starts. Let's take this point to be where the line ends. There it is. Now that we have 2 points, not saying the nice points, but the points nonetheless, we can get a slope. You know, your regular old change in y over change in x. There it is. We'll be referring to slope by m from now on. And while we're at it, why not just throw in the y-intercept, shall we? And if we take this as the origin, that's 0, 0. We'll refer to the y-intercept by b from now on. And that leads us into one of the more prominent equations for the line. Slope-intercept. There it is, right up there. Y equals mx plus b. And if we simply plug in the data we've gotten before, we come out with the equation for where this zombie is going. Now let's say we don't have a y-intercept, but instead we still have our 2 points. We can use point-slope form. Remember to leave x and y as variables. x1 and y1 are values from a point. And plugging the values in, there it is. Yet another way of expressing where exactly the zombie is going. And of course, you could multiply it out and set it equal to the constant to get your standard form. We have that right over there. But enough about that. On to something slightly more interesting. Not some picture on a screen. Now, here we have 2 of them, traveling in lines that are parallel. The lines are parallel when the slopes are the same. Nothing particularly fancy about that. It's when the lines get perpendicular that things get slightly more difficult. You see, the slopes of 2 perpendicular lines aren't the same, nor are they merely inverses of one another. In fact, for one line to be perpendicular to another, the slopes must be opposite reciprocals of one another, like in the example we have here. You know what? Perhaps it'd be better if I work one of the problems out for you. This shouldn't take too long. Let's start simple then. Here's a coordinate plane, and here are the x and y axes. Let's take a point at the origin, and 1, 2. And now we can figure out the slope of the line is the change in y over change in x. The change in y is 2, the change in x is 1 for this line. So the slope is 2. We have the y-intercept, where the line hits the y-axis, at 0. So there's that. As well, we have a point to use. So now, by substituting the data, we can get both point slope and slope intercept forms of this line. Of course, we can always factor it out and get standard form. Now let's try a parallel line. As I said before, a parallel line can have only one slope, the same slope as the line is parallel to. So, if we were to draw anywhere on this grid, any line with a slope of 2, excluding the original line, then that line is parallel to the first. Now if we were to try a perpendicular line, we simply need any line that's the opposite reciprocal of the first slope. Since the original slope was 2, the new line would have a slope of -1/2. And since it's only the slope that matters when determining a perpendicular line, we can place this anywhere, like here. As you can see, any two straight lines that don't have the same slope will eventually intersect. This point of intersection is very simple to find. First, you must solve for y in one equation. Then, substitute this new value into the second equation. You'll get the next value. Now, go back to the original and solve for x. Substitute this value into the second, and you'll get a y value. These two values represent the point of intersection, where the lines meet. I think I've got a visual example around here somewhere. Let me see if I can't find it. Ah, there we go. Intersection. Moving right along then, let's go back to our original line. And let's take a point, I don't know, over there somewhere. Now, we have a formula to figure out exactly how far that point is from the line. There it is. Now, as always, substituting in the data will tell you exactly how far this is from the line. There. And while we're on the subject of distances, let's discuss a locus. A locus is simply a set of all points that fits a given parameter. For our purposes, we're going to use distance. Let's say we wanted the equation of a line that's equidistant from both of these points here. To solve this would actually be quite simple. Merely set up the familiar distance equation, here, for both of the points. And, since we've determined that we want a line that's equidistant from both of these, set them equal to one another. Solving this equation will give the equation of the line we're looking for. Dr. Davis. What? What do you want? When can I come out of here? What are you talking about? I've been down here for a long time. You're the cameraman. I know, but I have been down here for almost an hour. So what? Dr. Davis, my feet are tired and so are my arms, and I think the zombies are getting mad at me. I can't say that I can blame them. But Dr. Davis... Alright, fine. Just stay in there for another moment, will you? Okay, if you say so, Dr. Davis. I will stay down for one more minute. One more. My goodness, I've got to pay more attention to who I'm hiring. Dr. Davis, can I come out? Shut up! Shut up right now! You're honestly getting on my last nerve. But Dr. Davis, I am so bored. There's something to do down here. I don't care! Stay down there! Oh, but Dr. Davis, I do not like staying down here. It's very hot and there's nothing to do. There's no space to walk. My legs are getting tired. They're very sore. My arms can't hold the camera up much longer. I am sitting here watching the zombies and they're not very talkative. They don't want to keep me company. That's it. They sit there. I'm going to have to kill him. Anything. Can't take this anymore. Dr. Davis, I am so bored down here. Oh, Dr. Davis, the zombies, they came off the rope, they're coming towards me. Dr. Davis, what? Dr. Davis, please, someone help me. Oh, no.
Dr. Davis. Dr. Davis, what's going on? What are you doing,
no,
Dr.
please,
Davis?
please
What's going on?
I'm shutting up this blabbering idiot.
Dr. Davis, don't let that man die. Oh my gosh, Dr. Davis. That man, he's dying. The zombies, they're
Oh, that's enough for today. Where's my tea?